Hello, welcome to the first video of Basic Radiographic Instrumentation course. This video is going to talk about the heat management in the X-ray tube. So let's refresh our memory regarding the X-ray productions. Electrons are emitted from the filament. Okay, the electrons are emitted for the filament. And also accelerated towards the anode. Okay, due to the high voltage potential between the anode and also the cathodes, so the electron gain a lot of kinetic energy. So the projected electron will strike the tungstens and interact with the atom in the tungsten and produce X-ray. However, only 1% of the X-ray photons, only 1% of the kinetic energy is converted to X-ray photons, and 99% into heat. This will make the tungstens very hot, and if the heat produced rise above the limits, the tube can be damaged. And the tube also can be damaged. Therefore, to prevent this damage, the radiographer must aware the quantity of heat produced and its relations to the heat capacity of the tube. Basically, the heat produced is lost or dissipated by radiations, conductions, and also convections. Most of the heat produced in the X-ray tube lost by radiation during the exposure, where the anode may glow and emits infrared radiations. However, some heat is also conducted through the neck of the anode to the rotor and glass envelope. This will also increase the temperature of the oil bath, and this will convect the heat to the tube housing and to the room air. When the temperature of the anode exceeds the limits, the melting anodes and printing of the anode can occur, and this will reduce the radiation output of the X-ray tube. If the temperature of the anode increases too rapidly, the anode may be cracked, and this will make the anode unstable in rotations. Okay. The heat produced in a single exposure can be calculated using this formula. The quantity of heat produced in the focus spots in joule is equal to kV, effective kV value, kilowatt volume, times MES, or waveform factor times peak kV value and time MES. Okay. The waveform factors depends on the generator used in the X-ray tube. There are different type of generator depending on the applications. So from this table, we can see that there's about 5 type of generator. So we have single phase with waveform factor 0.71, 3 phase 6 pulse 0.96, 3 phase 12 pulse 0.99, constant potential or high frequency 1.0. Don't worry about the type of generator. This will be explained in the next lecture. So the amount of heat produced can also be expressed by heat unit HU, which equals to 1.4 times heat in joule. Therefore, for a single phase generator, HU is equal to kVp times MES. And for 3 phase 6 pulse, is equal to 0.96 is the waveform factor for 3-phase, divided by 0.71 the waveform factor for single phase, times kVp times ms. So we get 1.35 times kVp times ms. Okay, this is for 3-phase 6 files. Sorry. So below, basically the heat in terms of heat unit is also equals to generator factor times kVp times mas. So this is the generator factor for different type of generator. Other than that, the power or the watts can also be described as the energy per unit time that can supply by the extra generator or received by the extra tube during the operation. So the power in watts is equal to waveform factor times kVp times me. Okay, this is the table of generator types, the power level usage, application, and also the power requirements in kilowatt. So for a single phase or single pulse or one phase, so the power is very low, the power usage is very low, less than 2 kilowatt, and usually in the dental, X-ray or handheld fluoroscopy units. For nowadays, most we are using a constant potential or high frequency. So for high frequency, the power level usage is orange, and all type of radiography procedure, the power requirement is more than 2 kilowatt, less than 150 kilowatt. Each radiography unit has a set of charts which help radiographer to use the X-ray tube within the acceptable exposure to avoid damage to the X-ray tube. This is to determine the operational limits of the X-ray tube for single or multiple exposures, and the permissible heat load of the anode and the tube housing. The capacity of the focus spot track is generally specified by the manufacturer in the form of graph or tube rating. So the parameters that influence the characteristic and the value of rating chart is the extra tube design, such as the focus spot size, the anode rotation speeds, the anode angle, okay, and the second parameter is the X-ray generator type. It's either a single phase, 3-phase, okay, or high frequency generator. Basically, there are three types of X-ray tube rating chart, which are radiographic rating chart, anode cooling chart, and housing cooling chart. Radiographic rating chart is the most important because it gives information which radiography techniques are safe or unsafe for the X-ray tube operations. So we can see as this is example of the radiographic rating chart, where each chart show a family figure representing the various tube current in MA. So this is a chart for one X-ray tube. We can see that this is the curve. Okay? The curve is the MA. Okay, the y-axis represent the kVp, and the x-axis represent the time. Okay, the difference between one chart to the other one, we can see at the below of the graph. Okay, the bottom here, we have for example, this is 10,000 rotation per minute, 3-phase anode focus spot 0.6 mm, and the angle is 11 degree. Okay, for the next one, we can see that it has 3,400 rotation per minute, single phase, 0.6 mm, and also 11 degree and angle. So every chart we can see its difference regarding the rotations and also the focus points. Okay, so the curve is represents the current. Okay, for a given MA, any combination of kVp and time that lies below the MA curve is safe, and if above the curve is unsafe. What does it mean by this safe and unsafe? Okay, let me explain to you. Okay, so we have, this is the same graph as previous one. We can see here effective focus point is 0.6, so this is the peak kilovolts, so this is the time, and this is the current. Okay, for example, okay, for example, I want to check if for example 60 kV, right? So yes, 60 kVp. Okay, I have 60 kVp. Time is for example 0.4 second. Okay, 0.4 seconds, right? Okay, for 250 MA. We want to check, we want to know if this the exposure is safe or unsafe. Okay, so we go to here. Okay, 60 right, 60 kVp, 60 kVp. Okay, we have the straight lines, and we have 0.4 seconds under this. Okay, so basically the point, the intersection between it is below the 250 MA. Okay, below the red curve, right? So from here we can say that this the parameters, okay, is safe, right? This is a safe exposure. Okay, for example, if I change the values, for example 70, okay, 70 kVp, 0.4 seconds, 250 MA. So I just change from 60 kVp to 70 kVp. So using the same technique, okay, 70, right, this is 70. Okay, same. Okay, 0.4 seconds. So we can see here the intersections is above the red curve, above the 250 MA curve. So this is unsafe procedure, or this is unsafe exposure. Referring to the previous figure, which of the following set of exposure factors are safe and which are unsafe? Okay, try to solve this. Pause the video while you do that. Welcome back. Have you solved these questions? Okay, let's look at the answer. Alright. Okay, so the first one is safe, second one is safe, the third one is unsafe, and also the fourth one also is unsafe. If unsafe exposure is made, then the tube might fail. However, nowadays X-ray system have a microprocessor control that does not allow an unsafe exposure. Alright, so you don't need to worry about this. Okay. The anode has a limited capacity for storing heat. Therefore, anode cooling charts contain information regarding the thermal capacity of an anode and also the heat dissipation characteristics. Compared to radiographic weighting charts, the anode cooling charts does not depend on the filament size or the speed of the rotations. Okay, this is an example of the anode cooling chart. We can see here from the figure, the maximum anode capacity is 350,000 heat units, and if the anode has the maximum heat unit, that means it will take about 50 minutes. Okay, 15 minutes for the anode to cool completely. Other than to determine the maximum heat capacity of the anode, the anode cooling chart is also used to determine the length of time required for complete cooling after any level of heat input. What does it mean? Okay, let's go to one example. The question is calculate the length of time it will take for the anode to cool from 350,000 to accept a series of exposure totaling 100,000 HU in a single phase unit. So this is the anode cooling chart. So we know that the maximum is 350,000. Okay, so the anodes now has the maximum value 350, and we need another 100,000 H units. So what's the time? Okay, what's the length of time it will take for the anode to cool down? So okay, so that's mean we have maximum is 350,000 minus 100,000. So here we get 250,000. So from here we go to 250,000. Okay, so the times required is about, okay, maybe somewhere here, sorry, maybe it's about 1.3 minutes. So it will take 1.3 minutes before the next exposure, that means the 100,000 HU can be made. So this is examples or question regarding the anode cooling chart. Next is the last chart is housing cooling chart. Similar shape of anode cooling chart, but it shows maximum heat capacity in the range of million heat units, and to complete cooling the housing after maximum heat capacity, it requires about 1 to 2 hours. Okay, this is an example of the charts. So the housing heat units, okay, nearly 1,250,000 HU, and the cooling times maximum is for this particular figure is 150 minutes. So I think that's complete our talk about heat management. So we have three type of charge that you need to know. The first one is radiographic rating chart. The second one is the anode cooling chart, and the last housing cooling chart. Okay, thank you, see you again.